All right, gonna try and re-record lecture 22 here since the recording got lost in cyberspace. Talk about stereochemistry of reactions. And the important things that I want to remind you of is that we said two things. So one is that in relation to stereochemistry and molecular properties. So one is that the physical properties of enantiomers are identical, except for the way they interact with plane polarized light. So and when we've talked about physical properties, we've typically said boiling point, melting point, spectroscopic properties, but this also includes the free energy. The second principle that I want to remind you of relates to diastereomers. And we said that diastereomers can, parenthesis, in principle, have different, or by definition, have different physical properties. In practice, sometimes those physical properties are too similar to measure. But if you sort of look close enough, they're going to be, if you look with high enough resolution, they're going to be different. So I'm just going to keep it simple and say diastereomers have different physical properties. And that includes free energy. So diastereomers have different free energies. If you measure the heat of combustion of two diastereomeric molecules, you get different values. Okay, and up until this point, we've only applied these arguments to stable molecules, okay? But what's important is that these apply equally well to transition states. So okay, and so this leads to several interesting principles about, or useful principles about the stereochemical outcome of reactions. And so I'll list those principles, and then we'll go through an explanation using a specific example. So Okay, so the first principle is that reaction of achiral reagents with an achiral starting material always generates racemic product if you're making a stereocenter, if you're making a chiral product. If you're making a chiral product, that chiral product is formed as a racemate. It is formed as a one-to-one, mixture of enantiomers. And so let's go to an example. Addition of HBr across 1-butene. Okay. And this reaction, previously, we've drawn it without any stereochemistry. So we typically just draw it like that, right? But in reality, this is a stereocenter. And so we need to completely describe this reaction. We need to actually describe the configuration at that stereocenter. And so the more complete answer is that you get a one-to-one mixture of enantiomers. Okay, so these two compounds are enantiomeric. And they're formed as a one-to-one mixture. And so another name for the one-to-one mixture is a racemate. Okay, and so we, this answer to this question is no longer acceptable. We need to start including the stereochemistry. Okay, and so there are multiple ways to do this, multiple correct ways to show formation of one enantiomer or another or both. Okay, and so when you're making a racemate, one way to show that is to simply draw both enantiomers as I've done here, and you can write one-to-one underneath. That's a bit labor intensive, and so the other descriptor that we can use that tells the reader that you're indicating a racemate is a plus-minus sign. So we can draw the molecule flat and put a plus-minus sign underneath. Okay, and so that sign tells me that I've got a one-to-one mixture of enantiomers, the dextro rotary and lever rotary, right? That's what a plus and minus mean. The other thing you could do, this is kind of, it's for the aficionados. We're not happy with these structures because that carbon, looks plainer. Another, slightly more sophisticated way to do it would be to draw one enantiomer and then put the plus and minus sign in there to indicate that you've got presence of both enantiomers in equal amounts. And whichever one you show is completely arbitrary and up to you. The key point here is the plus minus sign. So that allows me to just draw one structure, and it implies then that we've actually got the two that we're talking about. And why is this useful? This is useful because it shortens the procedure, but also because enantiomers have the same physical properties, if I then go forward and do reactions on these molecules, they behave in similar ways. And so it's a way to sort of emphasize the, to remind us of the similarity of enantiomers. Okay, so returning to this hydrobromination reaction, the question is, how do we account mechanistically for the formation of both enantiomers? Okay, and we know that the first step in this reaction involves protonation to form a carbocation intermediate. Okay, and I'm not explicitly drawing the proton that we introduced to the alkene because we're trying to focus on other aspects of the molecule. So I just abbreviate all of that as, or include that in that terminal CH3 group. And this carbocation, of course, is planar. Okay, and because it's planar, bromide can come in and attack either face of the carbocation. Okay, and so I can have Br minus coming in from the top, or Br minus coming in from the bottom. Okay, the carbocation is symmetrical with respect to that plane, and so it has no preference for attack on either side. Okay, and so what I want to do is think about what the transition states for those two forms of attack actually look like. And so okay, so if I attack sort of through pathway A, okay, I can draw a transition state that looks something like this. And again, the details are not as important as the overall geometry. You'll see why in a second. So I've got my Br, it's coming in and starting to bond to carbon. And the carbon, of course, is planar in the carbocation. As the Br minus comes in, it starts to pyramidalize a bit, so I can maybe push the substituents down a little bit. Okay, and the Br minus is approaching the carbocation. So some of the electron density on the Br minus is being transferred to the carbocation. And so what that means is that neither the Br minus or the carbocation have their full charge that they had prior to their interaction. And so we can abbreviate, it's a partial charge now. And so we abbreviate this delta minus, delta plus. From the standpoint of the carbocation, it's starting to accept electrons from the bromide. The overall charge is less than 1 now, less than +1. And from the standpoint of bromide, it's starting to donate electrons to carbon. And so its overall negative charge is less than 1. It gets closer to 0. So this is a rough geometry of the transition state. And I put the double dagger there to emphasize that it's the transition state. For pathway B, we can draw a similar, do a similar type of analysis. And so I will just draw Br coming in from the bottom. In this case, we push the methyl group and the other substituents up slightly. And this is delta plus, this is delta minus, and this is the transition state. Okay. So that is the transition state for attack from the bottom and the state for attack from the top. And so let me see. Does this have a select function? Yeah. See if I can copy that. So I'm trying to put this on the next slide here. All right, that didn't work. Let me redraw those two transition states quickly. So we said that we had Br, and then the methyl group going down. The ethyl group is starting to go down. the hydrogen's going back, and we said delta plus, delta minus, right? And then I drew the other one where I basically had the Br minus coming in from the bottom, so that was path B. So the methyl group is going to go up slightly. Br minus is coming in. Ethyl group is up. Hydrogen is back. Delta plus, delta minus, and double dagger. Okay, so those are the two transition states. This was A, pathway A and B, okay? And so the point here that I want you to see is that these two transition states are enantiomeric. And so if I rotate, if we rotate, we have sort of our XYZ plane, and I rotate the molecule in plane about this axis, right? I end up with a representation that looks like this. Okay, and so we do 180-degree rotation in plane, and that is the same sort of B transition state, okay? But hopefully what you can see now is that these two are enantiomeric. So we've only talked about enantiomers in the context of stable molecules. Sort of put that aside for a second and just think about this in general terms. We have one compound A on the left. We draw its mirror image, and if you try to superimpose them, you can't. And so though they aren't stable compounds, they are in fact enantiomeric structures. They're enantiomeric transition states. And so if we go down and think about our free energy diagram, now starting from our carbocation, okay, so that has some energy associated with it. And it's going to go down to form two products. So attack on the top face would give me this structure, and attack on the bottom face would give me this structure. Okay, and just to drive home the point, these are enantiomers, right? And so they have the same energy. Okay, and because they have the same energy, I put them at the same vertical height. So now we need to connect these two products via separate pathways, okay? And those pathways proceed via a single transition state, okay? And so we'll call this is the pathway A, okay? So this is product A, this is A double dagger, okay? And that the energy of that transition state has a certain location on the chart. And then we can draw path B, and what I need to think about is the position of B double dagger with respect to A double dagger. And is it higher, lower, or the same? And because those two transition states are enantiomeric, it is identical. Okay, and so we put it at the same level. And then going down. So this is B double dagger, and this is product B. Okay, so the transition states are enantiomeric. Therefore, same energy, right? And we know that the rate of a reaction is proportional to the activation energy. So this is delta G double dagger B. This is delta G double dagger A. And so delta G double dagger A equals delta G double dagger B. And so therefore the rate of formation of A equals B. They're identical. They form at identical rates. And so you get a one-to-one mixture. So basically this does I think this is actually a pretty good example because it illustrates the fact that these stereochemical principles apply not just to ground states, but to things that are, intermediates, to transition states, to things that are reactive. And so understanding, the interplay between stereochemistry and free energies allows you to think about the stereochemical outcome of different reactions. Okay. So give you another example, and this one involves come on. Okay, so this one involves the addition of Br2 to 1-butene, and we actually covered this for a little while in office hours, and so the lecture 22 office hours. So I'd encourage you to also look there. Okay, so we can think about how Br2 adds to 1-butene. And again, I can draw the product straight away. And this is, for example, how we would have drawn it before, right? We avoid stereochemistry. Draw it planar, but this center is a stereo center. Okay, and so in fact, the more comprehensive way to draw this is to draw stereochemistry. Let me get rid of that equivalent sign because that's not really what I want to say. And the question then is one, both mixture in terms of the two configurations. Okay. And so the answer is that I get a one-to-one mixture. These two structures are enantiomers. And so I isolate a racemate. Okay. And again, I could get to this conclusion using that shortcut that I mentioned at the beginning of the lecture. Achiral starting material plus achiral reagent goes to racemic products if you're making a stereo center. But let's work through this as we did the other one to try and work out a clean explanation for why this is the case. So we think about this mechanistically. The first step is attack of the alkene onto the Br. You cleave the Br-Br bond, and then you bring in a pair of electrons back down. And That alkene, of course, is planar, so I can draw it from a different perspective. And just like in the other case with the carbocation, where I had bromide attack either from the top or bottom, I can have the bromonium ion form from either the top or the bottom face of the alkene. Okay. And so I will draw those two structures here. And I'm actually going to stick with this sort of side-on perspective because I think it's a little less, hopefully a little clearer than trying to look at it. Try to look at it from the usual perspective. So there's one of my bromonium ions. That's addition to the top face. And there is, of course, an equally likely possibility that the bromide, the Br plus, bonds to the bottom face. Okay. And so again, if any of this gets away from you, fall back on your stereochemical principles. So I said this, it's equally possible you attack the top or the bottom. Why is that the case? Well, if you take either one of these bromonium ions, do an in-plane rotation of 180 degrees, you'll see that they're enantiomeric. And so enantiomeric bromonium ions, like enantiomeric compounds and enantiomeric transition states, have the same energy. Okay, and so there's no good reason why you would go for one or the other. And again, the simpler way to get to that conclusion is achiral reagent plus achiral starting material goes to racemic mixture. And so these bromonium ions have stereocenters. These two compounds must be, these two intermediates must be formed as a racemate. Okay. But anyway, let's think about the next step then. So in the second step of this addition, the Br minus is going to open the bromonium ion. And that attack will occur by backside displacement at the more substituted carbons. So remember that both of those carbons share the positive charge in the bromonium ion. The one that's more stable tends to have more charge due to hyperconjugation. And so we say that attack at that position by the nucleophile is favored. There's one other important point to make, which is relates to the stereochemistry of attack. The carbocation, we said you could attack on either side. Bromonium ion, remember, we don't do that. You can only attack sort of from the backside. And so you have Br minus coming in from the bottom in this case and opening up the bromonium ion, or from the top in this case and opening the bromonium ion that way. So let's draw those two products. Okay, again, we'll call these A and B just so we can keep track of everything. Call that A. And then over here, Br minus comes in from the bottom, or sorry, from the top. Structures like that. Br minus is down, Br is down. Get a structure like that, okay? And we'll call this B, okay? So those two products derive from those two bromonium ions. And the question then is, what is the stereochemical relationship between these two products? And the answer is that they are enantiomers. And so if you do an in-plane rotation by 180 degrees for either one, but say you do it for the molecule, make sure I get this right here. I think we want to go the other way. Yeah, we want to rotate the other way. Sorry. If you rotate, this way by 180 degrees, what you'll get to is the exact mirror image of what's drawn on the left. And so these two products are enantiomers. Okay, and so they are formed as a one-to-one mixture. Okay, and so we can put this, have a little bit more time here, so we can go a little bit deeper than we did in the original lecture. We can put this onto a reaction energy diagram to sort of get to this. And yeah, just want to make sure that we get everything covered here. The stereochemistry determining step now is not actually the bromide opening, okay, of the bromonium ion. That step is kind of locked in because of the stereochemical requirements. Okay, so you have to have backside displacement. There's no opportunity to have the bromide come in and open the bromonium ion from the same side. The step that actually leads to the enantiomers is in fact the formation of the bromonium ion. So we can generate a similar type of free energy diagram, except when we did the HBr addition, we started from the carbocation. Now we're going to start from the alkene and go to the bromonium ions. So okay, so we're going to have our alkene plus Br2, and I can make either bromonium ion. So let's say that we add from, let me just try to keep it in line with what we did before. Gosh darn it, I lost that slide. All right. We're going to add from the top. And we're going to add from the bottom. Okay. And this has an energy. This has an energy. There's a transition state associated with that. You get to the bromonium ion. And we already established that the two bromonium ions are enantiomeric. And so the barriers to get to the energies of the two bromonium ions are identical. There's only one energy for the starting material, of course. And so what that means then is that the activation energies to get there are going to be the same. So if we call this A and B, this is delta G double dagger A, and this is delta G double dagger B. And so, okay, so the activation energy to get to bromonium ion A is identical to that to get to bromonium ion B. And so what does that mean? It means in practice, the rates are identical and there's zero preference for formation of one over the other. And so you get a one-to-one mixture of those bromonium ions. And as I said, you then get backside displacement, and that kind of the bromonium ion sort of sets the stereochemistry for the next step. And so it's the energy of those two bromonium ions that leads to a racemic mixture. So we've gone through two examples, and this is going to quickly get more complicated in the next lecture when we talk about symmetrical disubstituted alkenes, but I just want to drive home the point that, there are two ways to sort of solve the stereochemistry of a reaction. The easy way and then the longer rigorous way. So the longer rigorous way is to work through the mechanism and ask yourself, what is the stereochemical relationship between the different possible isomers that I can generate? And as long as you're making enantiomers, you're making compounds of or intermediates or transition states of the same energy. The simpler answer is that anytime you start with an achiral reagent and an achiral starting material, you get a racemic mixture of products. And that derives from this idea, or that is basically capturing this notion that you're going to form all of these enantiomeric intermediates and transition states, and the energies are identical. And so there's no preference for one or the other. So I would memorize that rule, but then I would also, at least in the initial stages here, take the time to work through these mechanisms and convince yourself, that, the answer, if everything's achiral, you're going to get to a racemate. So convince yourself of how you get there. Show yourself that, the transition states or the intermediates are enantiomeric, the products are enantiomeric, so that you get a better understanding. And flipping these compounds around and reworking them, is going to just help you develop this, sort of the skill set to mentally manipulate them. And so finally, we covered a lot of this in the office hours, which did make it to the recording. So there's essentially another hour of this type of discussion available to you. And as I said, because this will tie in to lecture 23, which will happen in about 20 minutes, it's all sort of the same topic. We're not going to include this on the second exam. All right, so I'm going to very carefully stop the recording and hope that this doesn't get lost, so I don't have to do this a third time.